Hello, students. We've got some questions coming up out of the chapter review. So let's see what we've got here. Looks like we got question 27B. Okay, a tank that is a right rectangular prism, filled with water. What's the mass of the water in kilogram? Okay, well, that's pretty basic. We did one like that in class. So let's see here then. Suppose the tank is actually half full of water, and then a heavy metal sphere of radius 30 is put into the tank. Okay. Well, the metal sphere is 30 centimeters. Okay, they do tell us the height, which is good. They'd have to tell us that piece. Depending on which way it's tipped, the answer will be different because it depends on we're talking about kind of the area of the base. So the base does matter. And they tell us that. So what they're saying here is here's this shape. So what you want to do is think of the 3 meters being the height. Okay. And so you have 1 meter by 2 meters, kind of what we have. So this is kind of the shape that we have, something like this, a right rectangular prism. There we go. And it is half full of water. So the water line is here. Okay. Because it's exactly half full of water. Then you put a 30 centimeter sphere into it. Okay, well, that's going to sink to the bottom. So what I need is I need the volume of that sphere. Well, the volume of the sphere is 4/3 pi times the radius cubed. Okay. And so what we're trying to see is what's the new height, but what we need is that volume. So let's see here, 30 cubed. The 3 is going to go in there. That's going to be nice. So we're going to have 900. Let me grab my calculator. Okay. So we've got 30 cubed, so 30 raised to the third power, and then multiply that by 4 divided by 3. Okay. Okay, so that gives us 36,000 pi centimeter cubed. Now, everything else is in meters. Okay, so I'm at cubic centimeters. So if I think about King Henry's Dear Mom drinks chocolate milk. Well, I'm here. I need to get back to meters. That's 2, but we're dealing with cubic centimeters. So that's 3, 6 places. So 1, 2, 3, 4, 5, and 6. So 0.036 pi cubic meters. Okay, and that's helpful because now I've got everything in cubic meters. All right, now let's see here. Now I need to figure out what this is going to be in terms of the height. So let's see if we can do that. Okay. So what's that gonna look like? I need my base down here, right? So this is how much the volume went up. Okay. So the volume went up by this much, but the volume is 1 meter times 2 meters times the height measured in meters, and that has to equal 0.036 pi cubic meters. Well, the meters are all going to go away. This would be in meters as well. So now it's all just numbers. So this turns into a 2h 0.036 pi. Okay. So to find h, which is the height, right? How high did the amount go up? H is going to be 0.036 pi divided by 2. 0.036 let's see here, times pi equals divided by 2 equals, okay, so the height is now 0.0565. I'm going to round to 4 decimal places, so I'll change this into approximately meters. And it says, how high is the water now? And so the height now, well, remember, it was halfway before, so it was 1.5 meters before. So now it is 1.5565 meters high. Okay, so that's the idea. So again, take what they give you. They give you that it's halfway full. So you know it's 1.5 meters. Then all you're going to do is just solve for how far did it go up, which is like this height piece, because a little bit of water obviously got kind of bumped up because you got this ball that's now down here at the bottom taking up a lot of volume. So the volume had to go somewhere, pushes its way up, and we have a new height. So yeah, find the volume of that ball and then say, well, that's the amount of volume that changed. That's it. That's all we know. Volume changed. And then you could say, well, wait, I need base. So this is the area base times the height, and that's the volume of the rectangular piece. So what we're doing is finding the rectangular little sliver that we just got by adding that ball. Very cool. Very cool. Good question as well. Let's see here. Okay. Next up is 32, question 32. If the volumes of two silos that are similar right circular cylinders are in the ratio 2 to 3, the volumes are in the ratio 2 to 3. Okay, so now just let's go back and remember, we did some of this stuff in class. We talked about it. It's also in the textbook. So we want to make sure we're really, ooh, wrong color. Sorry about that. So we want to be really clear about how these work. These are ratios. So if we're talking about linear to area to volume, then like whatever that linear ratio is, then the area would be k squared, the volume would be k cubed. Okay, so if that ratio was 2 to 3, then the area ratio would be 4 to 9, and the volume ratio would be 8 to 27. That'd be the ratio. But now here, what they're doing is they're telling you the volume has the ratio 2 to 3. So you have to go backwards. Okay. So that is the idea. So now if we started over here, if we knew we had k squared to k cubed, this ratio right here, 3 over 2, is k cubed. So if you want to know what is k, we would have to take the cube root of this glorious piece, which is fine. It just becomes cube root of 3 divided by cube root of 2, and that is your ratio because they're asking you about the radii, and radii is linear. So there you go. Because remember, it's a number I'd have to cube in order to get to 2, a number I'd have to cube in order to get to 3. So your ratio would be cube root of 2 to the cube root of 3. 32. Let's see here. Oh, I do love these questions. I love them. I really do, because they're kind of fun. I think they're kind of fun. What advice would you give to someone? Would you have more of these? It's less expensive to have the small ones, or you would have a big one? Which one would be better? Let's check and see what the question is. Oh, it's 34. All right. All right. I'll leave 33 alone. And the following figure, quadrilateral ABCD, is a parallelogram. Okay. That's fine. So we have a parallelogram, and P is any point on AC. Okay, so AC is just a diagonal. Prove the area of BCP is equal to the area of DPC. All right. Let's see what we can do. So if we've got this shape, we want to prove this area up on top and the area on the side have to be exactly the same area. Now the bases are definitely different here because they just say it's a parallelogram. We don't know it's a rhombus. Okay. So let's see. So whatever it is, that base, I'd have this height right here. I could think of this height and this height going up. Okay. Hmm. also have well, I also have the total height of this shape, which would go from one point opposite and down. That would be the overall height of the shape. And so then that would be this length. So AD times H, oops, AD times H would be my area. Or I guess it's BC as well, or AB times whatever the H would be going this direction from that point over to that one. So there's H1 and there's H2. So the area would also be AB times H2. And P is any point on AC. Well, I don't know. I think I'm going to explore a bit first. So I'm probably going to open up GeoGebra. And I'm just going to build myself. Oops, wrong calculator. I'm just going to build myself that shape. So now I want I can pick any point out here. And then I want parallel line from here to there, right? And then I can make a segment from here to here. And I can do a parallel line from here to there. And then there'll be a point where those intersect. And I can make the final segments. Okay, so now I've got my parallelogram. If I put a point here, oops, it's got to be on the line. There we go. Then I build these triangles. Let me make sure that that works out. So polygon above right here, there's one, and here's a polygon below. And that's a good thing about having something like GeoGebra is you can actually go through and let's see your settings. Let's change the color a little bit. There we go. Okay. Stop that. Let's just escape out. Okay, so I've got two different pieces here. And if I go down to measure, I can measure the areas and they are exactly the same. And if I move them, I can see that they will always be exactly the same area. Okay, so in order for that to be the case, hmm, yeah, because we could build our height here and this link, because this link matters. And height. All right. Well, we've got at least the idea that they are the same no matter where we put them. And we know we know this angle down here is going to be the same as that angle up there. And this angle here is going to be the same as that angle over there. Because we won't actually have vertical angles unless we have a line going all the way through. So we don't have that piece. Yeah, this one's definitely making me think. Huh. Well, oh, and these letters are off, right? These letters off. A, B, then C, then D. Okay, so I got them all wrong anyway. A, then B. I wonder if I can just move this up here. Okay, there we go. Then move this one down here. There we go. Okay, A, then B. The C is on top. Okay, so I got those backwards. Settings, name, C. And this one here, we'll change the setting on it to be D. And then this point in the middle is P. Okay. Okay, so there we go. So now it does match what's there. Let me get rid of this. Let's see here, hide that. Okay, so hide that object, and we'll click on here and we'll hide that object too. Okay, there we go. Now we're back to what we have. Okay, okay. Oh, all right. You got two triangles. You're trying to prove them equal, but they have the same area. So it would be ideal. Okay. So here's what's going through my mind. You can take a point from P. This is what you at least kind of see what my brain's saying. From P, I can bring this down, right? And then I'm using this base right there. Does that make sense? But if I do the same type of thing over here and drop a right, then I have this base. So I have two different heights and two different bases, which is going to make things very, very challenging. So whenever I run into one of those pieces, I try to say, okay, is there anything I could use that would be the same? These two triangles, the only thing they have in common would be this side. So what if, I don't know, what if we try using this as the base for both triangles? Whoa, we are in a strange place. Okay, that went horribly bad. Please stop. Okay, thank you. Let's just clear all those. I have no idea what's happening. Can we not just clear all my drawings here? Okay. Let's stop sharing for a second, and then we'll start sharing again and see if it's still all there. Please, I hope not. Oh, it is. Okay. Let's just try undoing. Okay. Okay, we're back. We're back. All right. Sorry about that. I'm trying to use my annotation tools at the same time. The computer is allowing me to draw, apparently. So, all right. So we're going to treat this as our base. Okay. Then what we have to think of is, what is our height? Well, our height would be different. So if that's the base, the height would come from point D. So one height would come over here like that, right? And one height would have to come from this point and come down. Okay. So in order for these areas to be the same, we'd have to be able to prove, unless there's some other weird something going on, if we could prove that these two are exactly the same, could we? Could Oh, I think we could. Oh, I think we could. I think we could. I think we will. That's what's going to happen. Okay, let me make this a little bit bigger, just so we can do this. Let me turn off my annotation here, and then just come back over to move. Okay, so what I'm going to do is I'm just going to make this. Oh wait, let me clear all my animations. I'm going to make this bigger. I think this will help. I really do. But we're going to find out together whether it helps or not. Okay, so there we go. Parallelogram. Everything's going good. Okay. So now when you picture this, well, here's what I want you to do. I want you to think, I'm gonna treat CP as the base of a triangle. Now notice it is an oblique triangle, right? It's not a right triangle. And so it's tilted off to the side. So you have to kind of turn your head to see that CP is going to be the base. Okay, so right now I'm only looking at this triangle, this kind of pink triangle up here. Okay, here's your base down here. So extend the base and then drop a perpendicular down from the point until it hits the bottom. Okay, so that, I don't care, we can call that a new point. What have we used? A, B, C, D. So what, E, F, G? I'm going to call it X because I'm not going to deal with that. Okay, so BX. And again, we're going to call that H1 because that's the height of the first triangle we're looking at. Okay, then what you do is you go back and you say, okay, hold on, let's do that again. We're still going to use this CP as the base, but we're using it now for the triangle right here, CPD. So then we extend this one and we drop a perpendicular down. Now, this is where things are going to get a little weird because that one almost looks like a perpendicular. It really does. So what's great is I can move that point anywhere. So if we come back and say, let me stop annotating here so I can just, so I don't screw anything else up. I'm going to drag that point this way a little bit, just so you can kind of see that from here we need a perpendicular. It may be the line segment itself. It most likely won't be. And I hope that that kind of helps with kind of what we're doing next. Because now I'm going to grab and bring from this point, I'm going to go perpendicular. Okay, and so that becomes H2. So I have, here's what I'm looking at. Okay, here's what I'm looking at. This, it's a parallelogram, right? So I know whatever side link this is, it's the same side over there. Okay, so AB is the same as CD. Okay, so I know that side's the same. And I know that in these, this is where it's going to get a little strange, maybe. And that's why I said, ooh, I got so excited. I'm now looking at this triangle, and I know it's weird. Why am I ignoring the first triangle? Because I'm actually just care about the height. So I'm looking at this triangle that's blue, and I'm going to look at this triangle over here that's green. Okay, so I'm looking at those two. And what I'm noticing is they each have a side in common. And because it's a parallelogram, this angle at A would be the same as the angle at C because the lines are parallel. And each of these triangles also has a 90-degree angle. So that means we have angle, angle, side, right? And that's why triangle AXB is going to be congruent to, I need a point over here, I'll call it Y, to triangle CYD. Okay, that's angle, angle, side. And that means that BX, what we want the height. So BX segment has to be congruent to DY segment by CPCTC because we have congruent triangles. Remember, you can't do any of the CPCTC until we have congruent triangles. So that means what? H1 equals H2. And that is all you need because the area of triangle one, this great big, let me get rid of all of my other shapes now. Let me just erase all of these, okay? And I'll probably get rid of all that too. Okay. So what do I now know? Now I know that this height right here, this H1, the area of this triangle is the base CP times H1. But the area of the triangle next to it is CP times H2. And guess what? H1 is equal to H2. And when that happens, that means that you have the areas have to be exactly the same. They have the same base, they have the same height. And so based on that, we are good to go. And that's why no matter where you move this thing to, you will always get the same area. Okay, because we're using that same base. And then what we're saying is the distance from a point to this diagonal, it's identical. Very cool. All right. Hope that helps. Pushing the right direction. That last one was that was a little bit of a sneaky one, I think. Kind of snuck up on me a little bit. Mostly because I think, at least for me, it feels like it's in the completely the wrong chapter. But anyway, because it was all about these congruent triangles that we had to get. So I feel like that was more chapter 12, but they're integrating it into chapter 13. So we play along with the ride. All right, that's it for now. Hope you're doing great. If you need anything else, let me know. Otherwise, I'll see you soon. Off you go.